Okay, good morning, everyone. Today, I'll repeat this problem because it's an important one. I think you also got confused by my mistake last time. So this is a nice problem which will include many of the tricks in the frames. We have this frame here, and it's loaded by this force here and this force here. There are two obvious big tricks here. The 30 is at B. We don't know if when we dismember this truss, is it here, or is it here, or is it partially here or here? We really don't know, so we make an assumption. Last time I made the assumption that it is here. Today I'll show you what will happen if I put it here. And this is a very typical practice by engineers. I don't know when it's going, so I'll make an assumption and see how the system is going to be balanced. The second thing that you'll notice is that this is a structurally indeterminate structure. You have four unknowns because this is a hinge and this is a hinge. And no matter what you do, you'll not be able to find the CX and the AX. You'll always find that they are adding up to same amount, which will be 30. The other thing that I should note is that CY and AY must be in the inverse because most probably the moment of this force and the moment of this force is going this way. So these two forces have to make a couple this way. I made the assumption that they are going this way, and I'll see if my assumption was correct or not. And so if you want to find the reactions, that's very easy to find CY. And so I'll say sigma m equals 0. And I think we discussed this last time. Where should I take the moment? I want CY, so I should take the moment at A or at C. Am I right? And we discussed that which one is better? C. The reason C is better is because I know this perpendicular distance. If I go for sigma MC, that would give me this directly related to here, and I can find AY. If I go to sigma MA, then I'll either have to find this perpendicular distance, which is not that easy to find, or resolve this into x and y, and then find the distances. You can still do it, but it's going to take you a long time. And so if I say sigma MC equals 0, that means the 50 multiplied by 1.2, and this is negative. Do I have anything else? Yes, I have the 30 multiplied by 4. That must be equated by what? Remember, I'm dealing with this free body diagram. I did not dismember anything yet. So I have the moment of this, the moment of this, and then finally the moment of this, which will be AY multiplied by 3 equals 0. That will give me AY to equal 60. If you want to find CY, we can do that. I can find the vertical component of this. And so that would give me sigma Fy equals 0. That means minus 60 plus CY minus 50 multiplied by 4 over 5. Why 4 over 5? Because this is 4, this is 3, and this is 5. And so here, the cosine is 4 over 5 equals 0. That means CY will equal 100 kilonewton. So I found the reactions that I can find. There are two that I don't know. I'm also required to find the forces in the members. The first thing that I should note here, and this is a step that is very important in every frame is this member here. This is a two-force member. Why? Because there is a hinge here and a hinge here. Much like a truss, a hinge here and a hinge here, which means that there is one force here and one force here. For them to be in equilibrium, they must be on the same line. And because this is pushing this way, it is pushing this to the inside, which means it is fair to assume that this member is in compression. So this member is in compression. I would reverse it here and reverse it here. How does this help me? Well, because this is a 90 degree, it helps a lot here. If you look at this member, and let me show it to you in a regular beam, you happen to know that there is a force here, that there is a force here of 50, and there is a force here that is also parallel to it. So the only way this member will be in equilibrium, and this is like 1.2 and 1.2, the only way that this member will be in equilibrium is this. If this is also 50, and this is not only 100, but parallel to them. There's no other way that this member will be in equilibrium. Why? Because if you take the moment around this here, will be 50 by 2.4 multiplied by something by 1.2. This something must be double the 50. And sigma Fy would tell me that this and this must equal this, which means all of them are parallel, which can be very helpful in this regard, that I will say this is the external 50, this is the internal 50, and now I know this is 100. And of course, this is 50, 50, 50. Now, I intentionally did not put this here because I just wanted to put it now. And so this force here is going this way. It's going here this way. And this is point D. So now I know several forces. I have to toggle between the free body diagrams to find the rest. Which free body diagram should I go to? Let's say this is 1, and this is 2, and you know this is 100, and this is 60. Which one should I go for? Which one is easier to resolve? Who's for 1? Who's for 2? Okay, I would go with 2. The good thing about 2 is that this force is going through here. So if I even decide to take a moment here, that would be easy. But if you don't decide to take the moment, you still can also find the components of this force. So let's go with number 2. I think it's solvable. Am I right? Sigma Fy, so free body diagram 2. I'll say sigma Fy equals 0. That means 100, that's the Cy, minus 100 by 4 over 5 plus By equals 0. That gives me By to equal minus 20. So I made a wrong assumption about By. The free body diagram managed to find it to me. I'll show you here, if you decide not to change your free body diagram, how would you deal with that? Okay. So now I have the By, and what should I do? I want to find the next unknown, which is the Bx. So to find Bx, I'll say sigma MC equals 0. That will eliminate Cx, Cy, and this 100. So I'll say 30 by 4, and this is negative, minus Bx by 4. I'm sorry, this is negative, and this is the positive one. And then also I have Bx as negative moment. So I'm sorry, By minus By multiplied by 3. But I know By, so I'll plug Py here, and I'll put minus 20. So I decided not to change my free body diagram. Once I do that, I'll use the By as I got it with its sign. If you do that, you'll find that Bx will equal 15. And then you'll find sigma fx, Cx equal 75. So if you want to study this joint here, especially what's going on with the distribution of the 30, this is 15 and this is 15, which effectively means that effectively at B, there is 15 going here and 15 going here, which makes sense. The 30 is divided half and half. Okay? Not in all situations it will be this way, but in our case it ended up to be divided half and half. So that idea of putting the 30 anywhere and seeing what is the force that is balancing it by the joint B would give me the solution. Yes?
Sorry, how did you decide it was 15 and 15?
Well, this was 30, and this was 15. So when I remove this and say, what is the net force at B, I'm left with 15 here. And I check on myself, 15 going this way, 15 going this way. It is the original 30 that was applied to the point. Any? Yes?
Would those 15s now have to counteract each other in the opposite direction?
Well, effectively, the point is subject to 30. So the total force at B is not 0, it's 30. So effectively, that's what is happening here. How the 30 was distributed on this side or this side, in this case, it was equal. But effectively, any point here has a 0 force on it, so all the forces must cancel each other. But at B, it's a unique one. The forces at B must add to 30. Okay, I have another tough example, and then an easy one. Member in the middle is a 3-force member. And a 3-force member has to be in equilibrium. That means two things. Either all forces are parallel, or all forces meet at one point. And in our case, all forces were parallel, and I divided them 50-50, 100.
Where's point E?
Point E is this. So this is a plier that is being used to rotate or tighten or loosen a nut. And we want to know if the force at the end of the plier is 150 Newton, how much is the force exerted on the nut? Now, this is one advantage of frames, is that we can also use them for resolving and understanding machines. And so, especially in mechanical engineering, this is very important. So the first thing that I will do is to build my free body diagram. I'll have this. So we deal with every one of these joints as a hinge, which means each one of them has one force. But because I don't know the force, in 99% of the case, it is okay or better to use Cx and Cy. So I have here Cx and Cy. I reverse them here. I didn't make any mistake. But if you start here, these are the two forces by the plier on the nut. At E, they reverse to this system here. And then I do a hinge here, or you can call it a hinge or a pin. I put it here and reverse it here, put it here, and the forces. Did I make a mistake?
Sorry, shouldn't the bottom one be 450? On the bottom, on the third free body.
No, it's 150. Both of them are 150, because when you are pressuring on it, it's the same of two forces. So it's 150. Yeah. Did I make a mistake?
Isn't it AB 2-4, so just be
Yes. AB is a two-force member. So that's the key to the solution here, is that AB is a two-force member. And most probably AB is in compression. And the big mistake that I did here is that I did not draw AB. Okay? So that's the bigger mistake that I did, which is what is the member that is remaining, which is AB. And once you do this, you'll see, oh, there is a force here, a force here. I'm doing this, then this is in compression. And as such, it's pushing the other way to the other way. So we actually have here 3, 4, 4. And of course, this also counts as free body diagram 5. OK, so you are required to find the forces at E. Which free body diagram would solve this for me? What we want is EY, and I just want to know which free body diagram would find this to me. Do you want to come do it?
Oh, not at all. But I was going to say the first one is like one that, because you have a known and then you have EY.
OK.
You take the moment about C.
So you take the moment around C, you get this force.
Oh, snap.
Yeah. So you take the moment at C, you take this force. Am I right?
Yes. Well, you have to take into components.
You take the moment around A, you mean? Or C? Who is saying moment around A?
I would say C.
So we have A and C. Who is for A? OK. And who's for C? Not too many. OK. Well, if you take the moment around A, you will get CY, because these two are on the same line, and these here are there. You could still also get A by after that, because sigma fx will be equal to 0, so you'll find this force. And then sigma fy will get you CY. But where is that going to take us from here? Yes?
So you start with FBD3 and find FAB by taking the moment of T, and then use that for the first free body and take the moment of C.
Exactly. So the problem here was you have 1, 2, 3, 4 unknowns. You cannot solve this whole thing. Okay? So number 1 is not solvable. But if you take the third one, you have 1, 2, 3, you can find a solution. Okay? And as she mentioned, she's very smart. She said, we take the moment here. I'm not interested in dy and dx. They are not required. So I don't get marks on them. So I take the moment here, find this, go back here. I have this force. And I take the moment here, find this, and I'm out of here. As I said, it's all about strategy. Like the frame is basically trying to, the whole idea about this module is to consolidate all what you have known so far in preparation for what is tougher. Well, tomorrow we'll start on something called bending moment and shear force diagrams. They are in the supplementary notes. I advise you very much to read them in the supplementary notes and in the book. So let's forget about this and try to solve. I'll say free body diagram number 3, sigma MD equals 0. Okay, well, what do I know about this? I know this will be the y and the x. The x is going here, so this is the y. I'll find alpha first. So FAB sine alpha multiplied by, this is 30 by 0.3, and this is going this way, it's negative, plus 150 multiplied by 3070 and another 30. So 1.3 equals 0. That means FAB equal 1650. So this would be alpha, and this is FAB sine alpha, and I'm taking the moment here. So what am I missing?
Yeah, the equation. So if you get a positive value for FAB, right, then the FAB should be negative.
Actually, FAB is positive, and this is negative. So FAB will be correct. It's definitely in compression. Yes?
If you're not using FBD number 2 and 4, do we still need to draw it?
If you draw it, you'll get a mark. And so now I find FAB. I can go back to find EY from here. Okay? Yes?
Sorry, I just want to ask, what's the units of measurement? Is it in centimeters or?
This here is, like, let's say it's millimeters.
Oh, okay.
So that would be, yeah, because that's the plier, something that you can do it. So I go back here and find this. Am I right? Is there an easier solution? Is there an easier solution? Yes.
Can you just find the y coordinate at big E cancel out so you don't even need the entire result?
Okay, so what he's saying, I think, if you find dx here, which is basically sigma fx, and you come here and take the moment around C, this is in the same line. So this is the same line. You can immediately find EY. So let me draw this carefully. So I'll stay in this free body diagram and say sigma fx equals 0. FAB cos alpha plus dx equals 0. That means dx equal minus 1517. If you come here in this free body diagram number 2, sigma MC will equal dx multiplied by 0.3, and without changing the free body diagram, this is negative. And EY multiplied by 0.3 so I plug here minus 1517 by 0.3 minus EY by 0.3. That means EY comes positive 1517. Of course, you could go back to this and solve it. That's OK, too. The trick is, in most cases, it's the moment equation that would help you. But here, the sigma effects also helped me find this. Yes?
Isn't that like one extra step though? Because if you go back to number 1 and take the moment C, you know F would be, you know 150, then you're just solving for EY.
Yeah. Yeah. So what she's saying, you know this is 1517. If you take the moment here, you immediately get EY, and that's also OK. Okay, so both of them are fine. Does anybody notice anything? Yes?
You're getting a lot more force for such a little amount.
10 times. For 15 newtons, I got 1570. Oh, I'm sorry, 150 newtons. I get 1570. It's 10 times. OK, let's go for the easy example of the day, and this will be the end of frames. So this frame has a fixation at A and a roller at C. And it is only subject to a couple of 200 Newton meters. And we want to find the reactions and all the forces, which means the forces at B. So the first thing that I should do is to see if I can find the reactions. Can I find the reactions? Let's first define what are the reactions. I'll draw this free body diagram for the whole body. And that will be AY, AX, and MA reaction. And I'll say here CY. Can I find the reaction, any of it? Yes?
What's the distance 0.6 here, the first column?
It's actually 0.4. So this is the distance between C and A. So can I find any of the reactions, C, A, for the whole free body diagram? Any of them is findable? AX is findable. Yes. Sigma fx equals 0. That means AX equals 0. And that's about all what I can find in this free body diagram, because everything else is not that easy to find. So what will happen is I will dismember the system, and I will say this is going this way, CY 200 Newton meter, BY BX BX BY AY, and MA. Now, yes,
I just had a question. Why couldn't we find the moment, why couldn't we find the reaction force to CY if we take the moment at A?
fantastic. So let's do that. Sigma MA equal CY multiplied by 1, that's positive, minus 200 plus MA reaction, which you don't know. So it's an equation in two unknowns.
But if we take the moment at A, wouldn't that cancel out the reaction itself?
No, that's a concentrated moment at A. So the moment reaction at a fixation is a concentrated moment that you don't know the value of. It cancels AY, and if AX existed, it cancels them. But the concentrated moment there is something that you have to find. It's a value. Yes?
And that concentrated moment wouldn't equal 200? They're not,
No.
they're unrelated?
It's the reaction for all of what's happening here. And I'll show you it's not 200. So if I go here, before I draft A, X, and B, X, and BY, I should start thinking a little bit. Is it logical to have a BX? It's not. So I should not bother myself and remove that from my draft. And in terms of BY, is it logical to assume that's going up? No, it's not. It's going down. And so I remove this here, and I go this way, which means AY must be also going down. Okay? And if that's the case, BY and AY are going this way, and MA is going this way, I better reverse MA. So I reach that BY is going up, AY is coming down, so their moment is going this way. This should be going this way. Because AB is subject to two couples, one that is concentrated at A and one that is created by BY and AY. And now I can solve for free body diagram 1. Sigma MB equals 0. That means CY multiplied by 0.4, and that is positive, minus 200 equals 0. That means CY equal 500. Sigma Fy equals 0. That means By equal 500. And then in free body diagram number 2, Ay, sigma Fy will equal 0. That means Ay will equal another 500. And then I'll say sigma Ma equals 0. That means minus Ma reaction, which is the concentrated reaction moment, plus 500 by 0.6 equals 0. That means Ma reaction equals, it's like, I think it's 300. Yes. Now there are 3 points a smart student can notice about this simple problem. See, 3 lessons. Yes? No. None of them is a two-force member. There is only 2 forces here, but there is this big thing here. So it's not only like a force member, it's a force and a moment member. So that doesn't apply here. And if it was 2 force member, they have to be going through it. But there are a variety, yes, so they have to be in the same line. So a two-force member does not have a moment in it. If there is a moment, everything is thrown out of the window. There are a few things that a smart student should be able to notice here. So what happens here, this is a couple, and these two are another couple. So the two forces cooperated and made a couple countering this thing. And here, the same thing. There is this force and this force that has to exist. So they're making this couple, so the reaction get another couple against it. There's another 2 points that a smart student should also notice. One of them is nice and one of them is critical. Yes, sir?
Like, sort of like a pattern, but like the ratio between like the 0.4 and the 200 is equal to like the 0.6 and the 300.
Exactly. So the dimensions matter. This is a third point, and I'll leave that in the end to discuss. But there are 2 more points to discuss. The first, which is very important, is what we said before, a couple is a couple everywhere. Okay? If you are looking at this body, if you're looking at this whole body, you are looking for the reactions. Am I right? You then cut at B. And if this is the body, yes, this moment can move anywhere. But once you cut it and expose the forces, this is the body. And you still can move this anywhere, but you cannot say, let me first move this and cut the body. Okay? So it is relevant, the movement is relevant to what forces you want to find. If you were looking for reactions and say, okay, this is the whole body, yes, this external force, these external reactions, and this are one system, they can move, the moment can move. But once I dismember it, then this external force, and this external force or external moment are part of the whole system. And yes, you can move this up and down, it doesn't matter, but you cannot say, okay, well, a couple is a couple anywhere, I'll put it here. This is a system, and this is a system. So everything is relevant. If you are looking at the external forces, and this is external, then this is part of this big system, it can move anywhere. Once you zoom in, you can move it within the system, but not between this system and that system. The final thing, which he kind of alluded to, the dimensions, basically what we have here is this very strong structure that is acting as a support for this weaker structure. Okay? It's just like this. So this weaker structure needs something very strong to carry it. And so the BC is actually resting on AB. Okay? And the fact that we made this way too long got us to handle a 200 Newton meter with a reaction of 300 and a force of 500. So our dimensions were not that good. If I reduce the 0.6 here, then I will need a smaller reaction, because we said it's 500 multiplied by 0.6, that's 300. If I make it smaller, the amount of reaction moment will be smaller. If I make this distance also smaller, the amount of the forces required is going to be changing. Okay? So if I make this smaller, this is not going to be 500, it's going to be more. If I expand it, it's going to be less. I'd like you to consider this, but the most important one is the idea of a system. Where is your eyes? Are you looking at this thing as a whole system? Then you cannot be considering by and bx. You are only considering cy, ay, ax, and the moment here, you can move the moment anywhere. If you separate it into two systems, you keep this in its system, and this stays as it is. See you tomorrow.